So just give you a background so you know who I am, where I come from before I started the company. I've been doing this company for 7 years now, but this explains why I did it. And I spent 8 years working on a DSP called the Tiger Shark, which was, has anybody heard of the Tiger Shark?
タイガーシャーク聞いたことありますか？
Yeah, 1, 2, 3, as many people as are users of Parallella. That's good. So I've been very successful. I've reached 3 people with the Tiger Shark and 4 people with the Parallella. So the Tiger Shark was supposed to be a base station processor and image processing for video. And we worked on this with 100 people for a long time. We spent $100 million, and recovered very little of that. So it was a big failure. But technologically, it was quite nice. It was very complicated. We had 24 megabits of DRAM on chip in 2004. That was a big achievement. But it was very expensive, very complicated. And so in terms of performance and cost, it couldn't compete. This showed failure and complexity. And then I spent 2 years at ADI doing a very simple processor for CCD sensors. We made a lot of money on these chips. The digital design team was basically me and 1 or 2 other people. And I created my own RISC architecture and sold to everybody, right? Sony, Fujifilm, Canon. I don't know how many hundreds of millions of chips we sold until today, and the architecture is still being used. So my epiphany that I had was merging the two, right? I saw complexity is bad, very expensive. Simplicity is good, very easy to implement. Now, how do you get to performance if you're going to use simple processor? Well, then you need lots of them. And that's why I started the company. You want to?
It's okay. 今のちょっと向こうを見てもらうと分かるんですけれども、彼のこれやってくるアダプティブの前までのやってきたことの説明で、難しいこと、技術はすごかったけれども失敗した仕事の話、あと CCD の方はそんなに難しくはなかったけれども結構利益を出して少ない人数で頑張った話とかの説明です。
Good enough. So these are the kind of the progression up to Epiphany 4 that we've done. So first one I did was a simulation, and in 2008. So it was Synopsys tools. We did the layout. I did the layout, and basically this was still while I was working out of my basement. So didn't spend anything except time. And then Epiphany 1 was the first prototype. So at that point we raised $200,000. Still, I always say we. It was actually at that point just me. So I did the first chip prototype. It was a prototype. It wasn't a product, but it worked. And then after that, people saw that it worked. I raised some money, $1.5 million, and I could hire some people, do an actual product. This was supposed to be a product. One of our vendors made a mistake, so we had to do Epiphany 3. But they paid for a lot of the stuff, so it was okay. But Epiphany 3 is the one that you see today on the Parallella boards. So this was created in 2010 with a 65 nanometer process, which is today about 10 years old. So anybody who's impressed by the Parallella board, think about the fact that it's a 10-year-old technology. And how, what that says about the architecture. If an architecture can impress you with 10-year-old technology as fast as Moore's law moves, there must be something there. So this is the Epiphany 3, and it really works as a product. And then 2011, we did the Epiphany 4, which is a 64-core product. And in terms of bugs, it's a product. We could ship this in millions. However, there's a problem. We did it at 28 nanometer, and if you want to do low volume production, you can do it for a couple of $100,000. If you want to do full mask production, full volume production, high volume to get the cost down, it costs $3 million. And so we didn't have the money. So we have now a perfectly working design, we can do engineering samples, and we have, but we can't ship in volume until we raise $3 million.
エピファニーの歴史をご紹介しましたが、最初の方はまあちょっとあれなんですけど、今一番最後の方で、まあ今28ナノミリのもので大量生産をするにはちょっとまだお金が足りていないので、お金を一生懸命集めないといけないですね。
So that's the status. And basically what we found out was with about $2 million spent, we created one of the, actually the most efficient processor in the world, whereas other people had spent billions. But it turns out that we didn't do very much. We just did the hardware, which was the easy part. So we were still dying as a startup company. So that's why 2012, we launched this new platform called Parallella. And there was really two reasons for it. One was for us. We wanted to grow our software ecosystem. But at the same time, we wanted to solve the problem that we were having and all those parallel processor companies were having, that nobody was really writing software for parallel. There was no ecosystem. The whole ecosystem from the bottom layer to the top was all written for big SMP machines, shared memory. And so, what was the goal? The goal was, let's make parallel happen today, right? Let's be an enabler. And to do that, we need to build a computer that is inexpensive. So we set the price at $99. It needs to be good enough performance and, pretty usable, right? It's got dual core ARM on there. It's got 16 or 64 Epiphany cores, gigabit of RAM, gigabit Ethernet, gigabyte of RAM, less than 5 watts. So, specs are pretty good. And it needs to be available, right? So it needs to be generally available. It can't be something that you have to sign an NDA to get access to, or that you have to call up the company and fill out some form, and then maybe they'll give you one. This needs to be a distributor, right? That you can, put in your credit card number and buy one.
それで2012年にパラレラのプロジェクトを立ち上げたわけですけれども、これでやりたいことっていうのは並列処理ですね。パラレラをハプンで、それをやるのにお金がかかってもいけないし、手軽にみんなが手が届くものでできるのがいいということで、この小さいコンピューター、値段は$99から、あと電力消費も5ワット以下。で、それなりの、デュアルコアアームとか、エピファニーは16コア、64コア。そこそこの、機能で、並列処理を行うための、プロジェクトを始めました。
So again, the Parallella project goal, to build a hardware platform to democratize access to parallel computing, meaning affordable, open, available.
これ、今にも言いましたけれども、このアクセスが簡単で誰でも使えて、お手軽な値段、オープンソースなもの、そしてすぐ使える、手に入るということですね。
So one of the key decisions here was, let's make it open. And the first question is, why should it be open hardware? Why? And I would say still today, most people don't care, but they should care. So when we started, before we started this Kickstarter project in 2012, we were very paranoid. We didn't tell anybody anything that we had without an NDA, because we thought, our competitors, guys like Intel and NVIDIA, would steal our stuff. And then we realized that the damage we were doing to ourselves was bigger than the threat from our competitors. So openness is very good. So, why openness? For the developer and the customer, the big things, it empowers you, right? You're going to have access to all the information. So if you think of a program that you've had, maybe a software program, it's a binary blob, it doesn't work. What do? The only thing you do is call up the company that made it or the developer that made it and tell them it doesn't work and wait until he fixes it. If you have transparency, you can fix it. And in hardware, that's a very, very big thing. And second, it reduces risk, because if it's open source, the IP is out there. You can use it. As long as the chips are available, you can buy them from a distributor, then you can make it yourself. So It reduces risk and empowers. So it's a very, very good thing. Now, what about the makers, guys like us? You know, why is it a win for us? Why should we take a risk and expose our IP, our things that we work so hard to create to others? And for us, at least, this is from personal experience. One, it fights the fear, uncertainty, and doubt. In that, you know, we make these big claims, and then the first thing people, you know, go on, you know, Reddit or Hacker News or Slashdot or anything and say, these guys don't know what they're talking about. This is fake and things like that. And when you give them the information, this is ammunition. It's hard to argue with facts, harder at least. Very good thing. Reduces support burden. So if you have open source stuff, even if your documentation is not so good, even if you don't have good customer support, you can always point to say, look, it's all there, right? Read the manual or read the sources. It's better if you have the good documentation. It's better if you have good support, but you have at least a last line of defense. Much easier to collaborate. It's amazing how when we work now with big companies, and the first thing to do is say, oh, we need to sign an NDA. And then you need to sign into our FTP site to upload something. And I say, look, here's the pointer to GitHub. Just take it, right? Do something, right? So much easier to collaborate. And the fourth one, enabling the ecosystem. So let's say we make a design, a board. So we have the Gerbers, the CAD drawings, everything else up there. Somebody doesn't like it. They take that, they modify it. Now they make their own design or they make their own daughter card very, very simply. So there's leverage in that. The fifth one, free review. So during the board design, so this was a very transparent project. We released the schematics way before we did the actual tape out, and we had some people review the schematics and found a couple of bugs. So those are bugs that otherwise would have been in the product today. So this was very good. And finally, karma points, right? Very, very important. It's life is too short, right? I mean, if everybody can share a little bit of information, everybody can move that much faster. I mean, for me, it was the big thing was BeagleBone. That was the one where I learned a lot from, right? This is a big platform, completely open source, and the Parallella was my first board design. And so imagine your first board design. There are all kinds of things that you have to learn that may not be in textbooks. And the best way to learn is from a board that's shipped 100,000 units. So just paying that back, right? So just like we took knowledge from the BeagleBone, now we're passing the Parallella knowledge back to the community to learn. That was a long discussion why open source is important, but
じゃあどうしてオープンソース、どうしてこれが重要なのかということですね。で、使う方、ユーザーとか、デベロッパーの人にとっては、自分の手の入れやすいというか、エンパワーということで、自分がいろいろできるというところがあります。あと、リスクを減らせるところですかね。あと、メーカー側にとっても、最初の頃いろいろ、レディットとか、ハッカーニュースとかいろんなこと言われたりもしたりあると思うんですけれども、偽の情報に惑わされないようになること、あと、サポート自体は、オープンソースなので、ここにマニュアルがあるよ、見てねっていうことで紹介できます。あと、コラボレーションも簡単ですし、エコシステムも、気に入らなければ自分で持ってきて作り直して出せばいいフリーレビュー、フィードバックってそういうところにありますね。あと、大事なのがカルマポイント。これは人生短いよということでいいことをやって、フィードバックを返して、また新しいことを教えてもらってということになります。
So I'll go through these. Not a lot of talking, okay? But this is first power up. So 2012, we launched the project on Kickstarter, and actually, I mean, the project itself was very painful. I don't know if anybody here has done a Kickstarter project. There's a tendency for them to be late, and our project was no exception.
キックスターター皆さんご存知だと思いますけれども、大体最初に言ってた納期から遅れがちですね。
So, but the good news here was, we were supposed to ship 6,000 boards by May, but we we're already at that point late, and but we did power up perfectly, and we had a board working. It wasn't the board we wanted to ship. It burned too much power. It did not have HDMI working, and so we said we're going to spin another version. And in fact, there's we shipped in the end. We shipped 50 of these, and I think there's one guy in this room who used it a lot, but otherwise it wasn't put into very much use. Yeah.
この最初の50枚持って使っている方いらっしゃいますかね ?Who is using the first 50 board or one of us 50 board? じゃあこれは、最初の作った試作品なんですけれども、まあ、パワー使いすぎるし、HDMI は動かなかった。まあ他の設計は良かったんですけれども、ということで、最初の50枚のうちを使っている方、今日のプレゼンターの中にいらっしゃるということです。
So this is something that was very popular. I realized people love stacked computers, and so I'm gonna build more of these because it goes viral every time. So this is these are the Gen 0 boards in the summer that we built up, and this is a stack of 42 of them, and this at this point I knew this is going to work, right? So we had 42 computers running simultaneously, and with quite a few fans there because they were getting hot, but they were all connected to a switch, and with the IP addresses, and it worked. Now what we found out is we shipped these 50 boards to Kickstarter backers, and there was a problem. Only one was being used. Now that user was very good, out of Australia, and he did. I mean, he's an amazing developer. His name is Not Zed, or his call sign, and he's written up probably 50 blog posts about how to use the Parallella for image processing, ray tracing, FFTs, matrix multiplication, and this was his hobby. He would have his day job, and at night he would hack on the Parallella. And so that's what we expected. We expected everybody to be like him, and but it wasn't the case. Only 1 out of 50 really used it. And this is after contacting people and finding out what happened. But yeah, so this is I'll get back to this part. This is important.
ここで、42枚のボードを使ってクラスターを作って、これはちゃんと動きました。まあ熱かったりもしたけれども。最初の50枚っていう話がさっきありましたが、その中、50枚送った中で、まあ、1枚だけがちゃんと使われてますっていうことが分かったそうです。で、その1枚を使っている方は今日いらっしゃいますので、また後からそこのお話はします。
So, now, in order to build 6,300 boards for Kickstarter and also get this into general availability, we had to mass produce chips. And so we went out and did what's called a full mass tape out. And we ordered a lot of chips, and this is the chips coming back. We gave 50,000 chips coming back in altogether. This is only about 10,000 right there, so people asked us, what about ESD and moisture and all this kind of stuff? And we're like, well, but we're our own customers. We're putting it on the board. If it doesn't work, we throw away a board. So it's fine. But we had very good yield. We redesigned the package, and so this was a big success. At that point, we felt like, okay, it's gonna be all right. That was August.
これ2013年の8月なんですけれども、チップを発注しまして5万個作りました。この写真はまあ1万個ぐらいで新しいパッケージで作ったんですけれども、だいたいぶどまりが 90% ということです。この時はやったぜ、大成功と思いました。
So now, unfortunately, at this point, things were getting expensive. So because we've taken longer to design the project, and while we take time, engineers still cost salary, right? So the longer you take, the more things cost. And if you don't have enough money, you run out of money. Now you don't have enough money to ship and buy the parts. And so at this point, after we got the chips back, some of our vendors say, okay, pay, right? You got your stuff, now pay us. So we were in trouble. And fortunately, one of the big Swedish companies, Ericsson, came in and they put in a significant amount of money. That saved the project, saved the company as well. So this was, now we could start shipping and actually making good on our promises. But we'd already suffered damage. The engineering team had been let go. So basically it was down to me, one company. Of course, when you lose engineers, you lose knowledge. So it makes it even worse. I safely say this was the worst time of my life.
ですね、長い時間デザインいろいろかかりすぎたので、従業員にもずっと給料を払わなければいけないということで、お金ばかりどんどんかさんでしまって、もう会社もまた危ない感じだったんですね。そういうところでエリクソンの方からお金を入れてもらうことができました。これはプロジェクトだけでなく、会社も救ったということになります。それで、ここから再出発で、エンジニアとかみんないなくなってしまったので、自分一人だけの会社、自分一人だけの技術チームということになってしまいました。で、5000人まだお客さん余っていますけれども、もう人生最悪の時でした。
So, now things started. I use open source software. Sometimes it crashes. That's okay. Now we got the perfect version, right? This is the one with the HDMI working and everything else. Now this was kind of weird. So now we had the funding, we could buy all the parts, start production. Now we had supply issues. Some of the chips on the board could not be delivered by the companies that we used. So we're talking about multi-billion-dollar companies could not give us the chips that we needed, even though we placed a purchase order and they said they're going to deliver. That cost us a few more months. So this is one of the reasons why building hardware is difficult. It's so difficult, and producing in volume is so difficult. It's one thing to build 10 units for yourself or some small volume. Building 10,000 is production. Except it's the worst kind of production, because if you're building 1 million, everybody will talk to you. Everybody wants to work with you because it's 1 million. It's a lot of money. 10,000, you have to really work hard to convince people to work with you. So for us, working with these big vendors, sometimes they say, well, yeah, but you're a small customer. Why do we need to help you? In the end, they were very good to us, but we had some logistics issues here.
じゃあチップのところですね。チップを作って、供給の方でちょっといろいろ問題があったりして、なかなか届かなかったりということがありまして、それでも全部の出荷を、2014年の5月までに終わらせました。で、結果的に1年遅れたということになりますね。で、やっぱ少量のチップの発注っていうのはなかなか大きな、会社からは重要視もしてもらえないので、大量生産もなかなか難しかったということになります。最後の方ではもうちょっと話をしてもらえるようになってきました。
I would say one more thing. 10,000 at $99 doesn't work.
1万個のチップで$99っていうのはあんまりうまくいきません。
You need to make a decision. Either try to go for 1 million units and then you can make it for almost nothing, or make 10 units. Don't make 10,000.
もっと大量だったら$99っていう価格もありなんですけれども、1万個ぐらいだとちょっとあまり割が合わないということですね。
So in review, Kickstarter project started at the end of 2012, finished, all boards shipped in May 2014. So it should have shipped in May 2013, so it was a year late. But in the end, we finally delivered. And then after that, we were able to get the boards into some very, very good distributors, Ars Components, DigiKey. In the US, you can also buy them from Amazon. So the boards exist. We have about 6,000 of them in stock. So we should be able to be good for a while longer. So yeah, so I would say that this is the best part.
これ、キックスターターを始めた時から、その2014年に全部出荷したところまでのタイムラインになるんですけれども、最初の方は全然あれですが、最終的には出荷も全部終わって、今や、RS コンポーネンツさんとか Amazon とかでも買えますし、在庫も6000個ぐらい軽く持ってますよということです。
So here's, I mentioned that 1 out of 50 that turn on the board. As a hardware designer, my first reaction was we just have to make the hardware better, right? More impressive, then people will use it. So we went to the International Supercomputing Conference in Germany in 2014, last year. And we did a little cluster that you see up there. So 32 boards, with each board with 64 processors, 66 actually, 2 ARM cores and 64 Epiphany cores. So we had 2,000 CPU cores in the size of this size, 15 centimeters by 15 centimeters by 68 centimeters. And the whole thing, including the power supply and the switches and the processors, burns less than 200 watts. So 200 watts, 2,000 CPU cores.
これは去年ドイツで、国際スーパーコンピューティングカンファレンスというところで出したものなんですけれども、2112個のプロセッサーを合計するとあって、で電力が200ワット。で、サイズは 15×15×68 センチという写真にあるタワーのような感じですね。これすごくうまくいったと思います。
And so the result was we had a booth, presentations and announcements. There was no interest from the supercomputing community. Nothing. Because, and why, right? So now I have to go through why, how is this possible? And in the end, everybody chooses Intel. Not everybody. And the few percent that don't choose Intel, they choose GPUs. And so we're after GPUs. And when you look at supercomputers, right, and big data centers, what costs money? And they say, all right, well, energy costs money. They care about energy efficiency, or so they say. But at the supercomputing side, more so than the energy efficiency, the software costs money. Writing the software costs a lot of money. System administration costs a lot of money. Right? The software to run the system costs a lot of money. So if you look at the actual cost of electricity, the value that we have, the efficiency, they don't care. So that was a lot of work to find out that answer.
これはあんまり興味を持ってもらえず、最終的にみんなはインテルを選び、GPU を選び、その後ぐらいかなというところでしたが、もう、ですね、電力消費の面とか、あとエコシステムの面からもうちょっと考えた方がいいのにとは思います。でもどうして興味を持ってもらえなかったのかというところをちょっと考えなければいけないとは思っています。
That was enough about the past. Now, kind of, where are we today? What's the present? So this is the hardware that we have. So we have 3 versions of the Parallella board. We have basically small, medium, large. So the small one starts at $99 at Amazon. Unfortunately, it's only US pricing right now. But it has no GPIO, so it's really meant to just be a server that you log into. If you want GPIO, you buy the desktop version. If you want a big FPGA on it, you buy the embedded version. They have these very high bandwidth, high density connectors by a company named Samtec, but a very fine pitch, 0.5 millimeter pitch. And very few people know how to solder to 0.5 millimeter pitch. So we made a board called Porcupine. Anybody here know the Japanese for porcupine?
ポーキパインって知ってますかね？ご存知ないですか？ハリネズミですよね。ハリネズミ。
So basically, it's a way to bringing out all the signals from these very dense connectors to 0.1 inch headers. And then in addition, we have a company in England that does cases. And we were actually hoping for more people to design cases. One of the, like they do for Raspberry Pi, right? So we looked at Raspberry Pi and we saw, wow, Raspberry Pi Foundation, they do the design, the software, and the board, and then all these other companies do the cases. It's an ecosystem. So we hope that would happen, but for that to happen, you need to sell a lot more, right? You need to sell millions. So we've only sold 10,000, and so we have one partner company that sells cases.
これが今、アダプティバの製品なんですけれども、パラレラのボードと、先ほど言いましたポーキュパイン、ボードカードと、あとケースをみんなもっと作ってほしいなということで、ラズベリーパイはいっぱいケースを持っているので、パラレラももっともっと売れたらきっともっとみんなケースを作ってくれるかなと思っています。
But if you have a 3D printer, there's about 3 or 4 open source case designs out on the web right now that you can download.
3D プリンターがあれば、デザインは簡単です。みんな作れます。お願いします。
So on the software side, things are actually going quite well. And what's happening is the software is being built up with layers. So we built the hardware, right? So it's like a relay race. That's the way we envision it, at least. And so after you do the hardware, you need the plumbers, the people who build the software infrastructure, the operating system, or the libraries. And so we've had some really good developers from the community. MPI is a message passing interface from the supercomputing domain. I think he's maybe the best software developer in the world. I mean, he's absolutely brilliant and proficient and prolific. He's out of the US, and he's here done the OpenCL compiler. He's done his own Copper thread, which is a POSIX thread for coprocessors. He's done the MPI layer. And the MPI, the trick there is MPI usually runs on big processors and clusters. How do you run it on a small CPU with only 32 kilobytes of memory? So he created an MPI that works with 32 kilobytes of memory. Very, very efficient. Probably should pause. Okay. So he did that. OpenMP, another parallel programming model which does multi-threading using pragmas that you write in your code, was done in a university in Greece. And by the way, all of these are available. Just there are links on the Parallella.org, so you go download it. Most of them are open source or is about to be open source. And the idea here is somebody who wants to learn parallel programming, somebody who wants to research parallel programming can. All these people are basically parallel programming developer or researchers. Now, the next level up is using these to write parallel programs. So we have message passing, multi-threading, data parallelism, message passing, bulk synchronous, which is, I would say, type of message passing as well. There is a basic, which is kind of cool. So this guy did a basic interpreter and did some way of communicating between the processors, open source. So it's just cute, right? Very, very cute. And in addition, we know people are working on APL, Forth, Occam, Haskell at universities. Not released as a product, but they've run it. So to me, this is a big success of the project. This is what we wanted. We wanted to create an open, accessible platform so these guys can create the infrastructure that the rest of the developers need. So step one complete.
ハードウェアの後はソフトウェアということで、この、ソフトウェアを開発してくれる人たちがここにいっぱい書いてあるんですけれども、例えばそのデイビッド・リッチっていう方は、MPI メッセージパッシングインターフェースということで、他にも、どこだ OpenCL もやってますし、あとは何かな。ベーシックを作った人もいます。基本的にメッセージパッシングインターフェースが多いようですね。あとさらにはその APL、フォース、オカム、ハスケルのようなところはまだプロダクトというほどではないんですけれども、大学でそういうのをやっている方もいます。この辺は皆さんが何かプログラムを書きたいときに参考にとてもなると思います。
But it wasn't enough, right? So basically, we're building tools, and what we found out is that most people don't want tools, they want libraries. So I started an effort in January called the Parallel Architectures Library. And the goal here is for this to be like a standard lib, a C standard library for Parallel. So if you look at standard library today, whether it's math.ah or something else, it's all scalar, right? It runs on one data point. This is not what you need if you want to have the future be parallel. You need to have a library that expresses both data parallelism and thread parallelism in that library. And so, this is going to make the adoption much faster because most people, they do not want to program in parallel. They just want to get the job done with as little energy as possible. So we started this in January. We have a bunch of functions. Some of them are completed, some of them are not, and I'll get into that later. Right now, we have 5 contributors to this project, 2 from inside Adaptiva, me and Ola, who's here as well, and 3 from the outside. One of those contributors is from one of our customers in Sweden. The other contributors are people we haven't met yet. So it's looking pretty good, pretty promising.
で、ツールよりもやっぱりライブラリの方が皆さん使いやすいということで、今年ライブラリを発表しまして、ここまだできること、できないこと、いろいろあるんですけれども、5人のコントリビューターで作業しています。2人はアダプティバの中のアンドレアスともう1人。で、あと、他の3人というのが、2人は会ったことなくて、もう1人は、やっぱ、パラレラを使っている人です。
So, So this is really meant to be, I mean, in terms of the API, it's generic. I mean, it's very generic. It should be able to run on SMP machines, SIMD, Epiphany. In terms of the code, right now we're writing C code. So it's decomposed of small kernels that are single-threaded. So if you imagine a sine function, the inner kernel is running sine on one data point, but then you need the thread parallelism depends on the architecture. So if you want this to run on a GPU, then the library needs to work in OpenCL or CUDA. If you want this to run on an SMP, you need to use POSIX probably. If you want to be very portable. If you want to run it on Epiphany, then you need to do something else. So there needs to be something in there that will choose based on the architecture that it runs on. That basically that ugliness needs to be hidden underneath the API. The user his program will be generic. He calls a library function sine, right? Sine function. And then he gives that a input pointer to his input data, a pointer to his output data, and he says, how many threads and how many data points are there in my vector. That's his interface. But the library itself, the underlying code, right now it's all C code, right? It's a C library, but the actual way of expressing parallelism for each architecture is going to be different. There'll have to be some if-def statements or something in there that will target the right platform to compile. So write once, compile many times. But write once with if-def statements or something. Yeah, I mean, right now it's just C code. So we haven't gotten as far as writing the parallelism part. It's actually only the C kernels. Yeah, so one thing here, one of the problems with having an architecture with 32 kilobytes is you can't link any libraries, right? Because the libraries that are there are too big. So we tried to link in like mathlib, right, from newlib, and one function and memory blows up because the functions are too big. There's too many check the exception. Is it invalid? Is it overflow? Is it underflow? Let me run in this mode and let me do this and that. Before you know it, one function takes up 4 kilobytes. Where if you wrote it in assembly, it would be maybe 60 bytes, right? And so if you write it in C, it won't be 60 bytes, but it might be 500 bytes. But that's a lot better than 4 kilobytes. Just the code density is a reason. That's what we started with, right? Just making a math library that is denser than the standard libraries are out there. There isn't an open source, widely adopted math library. I think we can. So now, where are we today with the numbers? We've shipped 10,000 boards all over the world. We have about 6,000 boards in stock. So we're working with 200 universities in total. We've donated boards to 100 of them. The other 100 have bought on their own. There have been 17 papers written so far, and many, many more will come this year, I expect. So it's the ecosystem here. Academic research is growing. There's 16 open source projects right now going on GitHub that are examples that you can use to write your own. Like you saw, there's many open source programming models that you can use. The forum is quite active with some very, very good people on it. And so it's a good start. It's not enough, but it's a good start.
数からちょっとパラレラどんな感じというところですね。1万枚以上の、ボードがもう出荷されていて、6000枚ぐらいは在庫を持っていて、200くらいの大学と一緒に、ボードを使ってもらったりとかしています。で、学術文献的なの17個、あとオープンソースコミュニティが16で、プログラミングモデルのサポート11件に、あとフォーラムが結構活発で1万2000以上のポストがもうされています。すごいいいスタートになったと思います。でもまだまだ。
So now, what about the future? And the best part I saved for last. So this is not the best part, but so this year, what we're going to focus on, first thing is software. So the Parallel Architectures library. So we can make all this performance that you have, the parallel performance, we're going to shortcut, right? So some developers will work on it, but once we get a library, then it becomes usable for more people. So Parallel is a very important thing. Second one is focus in on 2 areas. So I said supercomputing is kind of dead to me. It's it's not our area. Our area is embedded, and 2 areas specifically is SDR, so software-defined radio communication, and second one is imaging, so computer vision. And to me, these are very fun areas, very active. Now that we have so much performance, and we can run these things off a battery. Right? This really enables new application. If you make it small enough, cheap enough, what can you do with it? Imaging is anywhere from robotics to drones to autonomous drive, right? This is all computer imaging. We can definitely help here. SDR is cognitive radio, the ability to do any modem on any frequency in the blink of an eye, right? Just switch the modem out in software. This is pretty magical. So this is what we're going to do this year. We're going to make sure we have all the hardware in place, all the drivers, all the infrastructure, so people can do this application. Third one, which I hope I have time for, one of the things I promised as part of the Kickstarter was to write a book about parallel programming. I don't know why I promised that, because I'm not a programmer. I'm a hardware guy. But I'm gonna make sure it gets done. Whether I write it or I get partners to help me write it, it will get done, and it's going to be up on GitHub, so it's going to be completely open source. So that's the education part, and then finally, as a company, Adaptiva will be working on Epiphany 5 this year. So even though Epiphany 4, the 64 core, hasn't gone into production, something else will. I can't tell you what it is, but it's going to be big. Okay.
じゃあ、2015年の計画なんですけれども、まずソフトウェアは、パラレラアーキテクチャルライブラリーですね。さっきちょっと説明しましたけれども、5人でいろいろライブラリーを書いています。それから、自分の中ではスーパーコンピューターというのはちょっと終わっていて、STR とイメージングに力を入れていきます。STR、ソフトウェアデファインドラジオ。あとイメージングっていうと、ロボティクスとか、ドローンとかいう方向にも使っていけると思います。で、ティーチング、キックスターターで、プログラミングの本を書くとなぜか約束してしまったので、ハードウェアの人なのにこれを書きます。で、出来上がったら GitHub でオープンソースで皆さん見ることができるようになります。あと最後に会社としては Epiphany 5を作っていきます。
So we said, now that we have the hardware platform, what's the next goal? And this is the goal I think we need to get to. How do we make parallel programming easy and fun?
はい、じゃあ次のゴールは、パラレラ並行プログラミングを楽しく簡単にしていくことです。
So if we look at two incredibly successful hardware platforms, the Arduino and the Raspberry Pi, I think what they did is Arduino made programming fun for people who hadn't done programming before. Raspberry Pi makes computers fun for people who maybe want to get in and hack with them to a level that maybe hadn't been done before. So you make it easy, make it fun, then you get people to use it.
Arduino と、ラズベリーパイっていうちょっと同じようなちっちゃいボードコンピューターがあるんですけれども、Arduino は、プログラミングしたことない人に対しても楽しくプログラミングをできるような機能を提供していますし、ラズベリーパイは、コンピューター自体を楽しいものとして、子供から大人まで扱えるようなものにしています。で、このあたりを、パラレラでも追っていきたいと思っております。
So if you're interested in taking part in the project as a contributor, I mean, we always want people to work with, and that's how we set it up. So there's really 4 things that you can contribute to. You can contribute anything, but if that we run, right, as projects. One is the Parallel Architecture Library. Another one is our Open Hardware Library. So this is all the hardware description code that runs the FPGA on the board. This is really meant to be production quality hardware design, which today there is not very much of on the internet. And examples. And finally, education, right? How do we teach people to program in parallel? And this is something that, for me personally, I know is difficult. I'm more of a inventor and developer than I am an educator. So there are people who can do that much better than me. So this is definitely a place we need help.
じゃあこれから、皆さんここにどうやって貢献できるかということなんですけれども、一番上のパル、さっきの、パラレルアーキテクチャライブラリーと、あと、オープンハードウェアライブラリー、あとは、エグザンプルということでいろんな作例とかですね、あと最後に教育、どうやってプログラミングを教えていくことができるか、この、リンクのようなところで詳細を見ていただけます。
So, if you're interested, I think this is a pretty big slide, right? This is like a TED Talk kind of slide. But if we look at the history of the universe, there was no computing, and then we have von Neumann computing, and then we have from now until the end of the universe, which will be parallel computing. So the question is, if you want to be part of creating that ecosystem for the future, the way we do things, right? The method of programming computers for the future will probably be driven by whoever makes the language that takes off. Languages are very sticky, whether it's a computer language or a spoken language like English. Once it sticks, that's it. That's the language, and it'll last forever. And so in this case, let's make sure we get the language right. Let's not make it be JavaScript, okay? Make it be something else. Okay. Some announcements, right? This is the first time we're talking about some of these things. Some of we pre-announced this week. So first announcement. This week we launched a new computer called Supercomputer.io, and the idea is, what if we could crowdsource a supercomputer? The idea is everybody has their Parallella board. For now, it's only Parallella board. Maybe someday it'll be other single board computers as well. But it has their board lying around at home. They don't use it every day. They use it for projects. But in the meantime, it only burns 5 watts. Why not make it do some work? There's 5 million Raspberry Pis out there. That's a lot of computers. There's 10,000 Parallella boards out there, with each one with 18 cores. That's 180,000 CPU cores. What if we could keep this computer on, basically distribute a supercomputer all across the globe, and then have people use it? It's pretty significant processing power. So we're running this experiment right now. It's us and a company called Resin.io. And they have this Docker-based, container-based method of doing distribution. So basically, there's on the SD card, you have a Yocto-based, very, very basic Linux image. And then you send in an app to that. So you have a Yocto image with a supervisor. And then from a server running up in the cloud somewhere, you say, I'm going to push out an application. And so the way we did it, we basically asked people, download an image, burn it on an SD card, put it in your computer. Now we have a dashboard up on Resin. We see all these people's computers, right? Not their home computers, but their Parallella computers. And then we have an app that we're going to run. Then we say, distribute app. And then it gets broadcasted to every computer on this network. And then we push another button that says, go. And now it runs. That's pretty cool. We built a distributed computer. And today, I just sampled this before this, we have 2,500 CPU cores in this computer. But the limit is, again, 180,000 if everybody would sign up and put the computer on the network. This kind of crowdsourcing resources, I think, has some merit. So we'll see where this goes. It's a nice experiment. If we, arguably, it's the most efficient computer, supercomputer in the world. If we get, but at 2,500 CPUs, I wouldn't call it a supercomputer yet. But if we can get 180,000 or 1 million CPU cores, yes, it will be a supercomputer. That's the first announcement.
最初のお知らせは、supercomputer.io というのを立ち上げまして、みんなが家に持っているパラレルを空いてる時間、ここに使って、クラウドでスーパーコンピューターを作りましょうというものです。で今ちょっと見えているように2590個ぐらいの CPU が動いているはずです。で、自分のところでプログラムを、皆さんのところにプッシュして、またこっちに返してもらったりとか、スーパーコンピューターというにはまだまだですけれども、もっとこれが何万、何千何万と増えていけば、もうちょっと強力なものになっていくのではないかと思います。
Now the second one is I talked about software-defined radio. And so there is a very good radio platform called FCOMS from Analog Devices based on a chip called 9361. And basically it can do 70 megahertz to 6 gigahertz and sample about a 50 megahertz bandwidth in there, 12-bit resolution. And this enables software-defined radio. I mean, if you can imagine what you could do if you can just get direct sampling of a band in that, and then push it into digital, store it in DRAM, and then start doing your math, start doing your signal processing. Use things like GNU Radio, which is an open source framework that is very popular. You can imagine what people could do with that. You can do direct links. You can do microwave. with a down converter possibly. You could implement possibly GSM, LTE, and other things. So it's going to be a pretty cool toy. And so where we add, we've added something here. These things are already for sale, the FCOMs from distributors, and I think there are many thousands of them have been sold so far. So instead of trying to make our own RF board, which is complicated and expensive, one of our customers actually made an adapter board. And so you have the Parallella, you have an adapter board, and then you have the RF board. So we're going to be selling this in distribution quite soon. Right now we're building them up. Ola is going to show a demo of this setup at 5:30 with a kind of a virtual spectrum analyzer and radio working on this board.
2つ目のお知らせがこの新しい SDR のことなんですけれども、アナログデバイスの FCOM2 というボードがあるんですけども、これを使うための、アダプターボードですね。こちらの方をもうすぐ売り始めますよということです。で、これのデモは後ほど見ることができると思いますので、皆さんまた興味あったら見てください。
I mentioned the porcupine. So we now are building up 1,000 porcupine boards. So we really want people to use it. We have one of the things we've added here is a Raspberry Pi camera connector because we really like the camera module for the Raspberry Pi. It's inexpensive. A lot of people have them. And so now there's one problem. We don't have the drivers, and we don't have the FPGA logic to interface with it. And so we thought we'd do something fun. Instead of us going away and working on it, why don't we give a reward to the first person that can show a camera working and puts up the drivers? So inspired by a company called Adafruit that did this with a Kinect sensor a few years ago. They went out and said, the first person to do an open source Kinect driver gets $1,000. And so we want to do that here too. So the first person to use a Raspberry Pi camera module to take pictures with a Parallella, $1,000 reward. Okay?
これさっきちょっと説明しましたポーキュパインなんですけども、ラズベリーパイのカメラをつないで使えるようにということでコネクターがあります。でもまだラズベリーパイのカメラは動いてないので、これを一番最初に動くようにできた方には$1,000が待っています。ぜひ作ってください。
So, the fourth one is another experiment, I should say, in crowdsourcing. Again, this is completely open source software. We're not really paying for labor here, right? This is just trying to get people going with open source software development, right? People's time is very valuable, and so why don't we give some back? So we, basically for every function that somebody contributes to this library, we donate a Parallella board. We'll see if that motivates people. Right now we have 5 contributors. If we say that it doesn't work, just so you know, you contribute a function to this Parallel Architectures library, which is meant for all architectures, not just the Epiphany. You get a free Parallella board.
パラレラアーキテクチャライブラリですね。ここにファンクションを作ってくれた人には、パラレラのボードを差し上げます。
There's a list. Yes, yeah. There's a list. Yes. There's a list in there, and it's things like sine, cosine, arctangent, Fur filter, Sobel filter for image processing, Gaussian filter box. It's useful things, right? So we picked those functions as a first list. I would say if somebody wants to contribute different function, just ask, right? But yeah, I made up a list that I thought was the most important to start with.
はい、作ってほしい関数ファンクションには一応リストがありまして、その中のものを作ってください。
This is why the terms will be very specific, okay?
ここに書いてある通りですね、そのリストになっているものを作ってくれた方にはということで、それ以外のものを作っちゃった人は一応聞いてみてください。
So the last one, this is something that hasn't been going for very long, about 2 weeks now. It's mostly been Ola and Resin.io doing this work, and it's trying to showcase what you can do with Epiphany and also what you can do with Supercomputer.io. And I know the Resin guys are still working out the last kinks in the system. Ola is done with his work, and we should have a demo of this at 5:30 as well. But basically what it does is it takes a test image, right, to compare it to, and then it takes a library of 10,000, in our case it's 13,000 images, but it could be millions of images. It broadcasts this image to all the computers out there on this network. All the computers run the same program, which is this over here. And then basically each computer gets a subset of the total image database. So if you have, let's say you had 15,000 images and you have 15 computers, each computer gets 1,000 images. And then you just do brute force, right? You do a correlation, a 2D correlation of image A, image B, and you see who has the best match of all the images. And you say, this is the image. And you say, okay, I found the image. This is the best match. Now this is we're doing this with images. As you know, whoever here is into computer vision would say that you probably wouldn't do that in real life because you have scaling issues, noise issues, rotation issues. But what everybody does use, who does high-speed stuff and high image, is FFT. So you can see this is a kind of an example of what you do with FFTs. But it's all open source. I think it's going to be a good reference design. Ola went from doing I think it was 2 images a second a week ago to 280 images a second this morning. So, he's very good, and but it shows the optimization to go through how you get from very slow performance to very fast performance on the Parallella board. So, what does this do? Like I said, it's a correlation between 2 images. We're using FFTs to do fast convolution, basically. So if you remember your signal processing, you can do multiplication in the frequency domain between 2 matrices by just doing point multiplication. So 1 by 1. So you don't have that n cubed processing penalty that you have if you were doing just a matrix multiplication based or sum of products based faster, because FFTs are n log n.
これ画像認識で、これ後ほどまたデモをお見せできると思いますが、テストって書いてある1枚の画像ですね。こちらの方を他のデータベースにある13000とか書いてある大きな、データベースのイメージと比較して、どれがマッチするかっていうのを探し出すものです。で、処理としては、280枚を、毎秒処理をしたり、で、オプティマイズに関しては、ちょっと早くなったり遅くなったりというところもありますので、そこはなぜなのかっていうところも探しつつ、今続けているところです。で、280っていうのは今朝の数値だそうです。
So yeah, so that's what I have for today. Yeah. Yep. Yeah. So yes. So the challenge there has been just a time conflict and resource conflict. And I would say that the specs are open, the chips are available, and so anybody who wants to do their own board or do a cable can. I think for us, our focus more now is on the software side. If you look at the software-defined radio, the imaging, 16 cores is a lot for a pretty big set of problems. And what's beyond that, well, for that, we're working on Epiphany 5. So the kind of in-between, let's try to bridge that, hasn't been a focus area. So yeah, so I think until now, one thread per core has worked really well. Cores are almost free. Yeah. So, you know, there is, in terms of technology, there is what we have now, which is, I think, a good platform for certain classes of problem. If you're talking about massive parallelism, then there is the stuff we're working on. Because in the future, cores will be virtually free. 1,000 cores is gonna happen, right? I mean, it's easy. As we scale down, there will be thousands and then tens of thousands of cores on a single chip. At that point, you know, is there a point in having more than one thread per core? You know, you just say, look, I spawn a thread by putting a thread on the neighboring core, maybe, right? So I think the one thread, maybe 2 threads per core is a good model, but not massive number of threads per core. Yeah. But I think we're always going to be memory limited. Okay.
後でご質問ある方は、後から、懇親会なり、途中休憩なり捕まえてください。If you have any questions, we'll catch up him after the session. And thank you very much. And yes.